All right. Hello, everybody, and welcome. Sorry we are running a couple minutes behind tonight, but let me turn down the music a little bit there. So, we're running a few minutes behind tonight. Just had some issues to work through before I could go ahead and get started, but it looks like I think we're good to go now. Let's see. I don't, though, see the camera for some reason. Does not look like it's working, which is strange. Looks like it's working there. Not sure if you guys can see the camera or not. If not, I might just have to do without it tonight. I'm not sure why that would have stopped working. Let me try a couple settings here, and then if this doesn't work, then I'll try something else. Okay. It might be because I have changed desktop environments. So maybe it doesn't like what I've got going on here. I'm not sure. I'm going to move on for now and go ahead and jump into the stream because we have a lot of ground to cover tonight, and I wanted to get through as much of that as we possibly can. So, with all of that said, before we jump into the content tonight, I do want to take a quick second and thank the supporters of the channel. So that starts with our partners, who are the highest tier of supporters on Patreon and YouTube. Those are Adarcia, Gerbolis Inc., Patrick Kuhlman, and Wen Chang. I'd also like to thank the other supporters here on the screen. They are the other members of Patreon and YouTube, as well as Twitch subscribers. Can't talk tonight, apparently. So I really greatly appreciate all of the support there. Of course, if you want to support me, you can go to patreon.com/TravisVroman or join my YouTube membership. So I'd also like to take a quick second and thank everybody else who follows me here on the stream, comments, or watches on YouTube. Thank you all for following along. Your support is greatly appreciated. Okay. So, I guess since we don't have a camera tonight, I will proceed with what we are going to talk about. So, since last week, we have actually put in some additional changes. Let me see. So last week we refactored the render view stuff, and I believe we also started on some stuff for a Gizmo. So let's see. Let's go ahead and take a look at those changes first. So give me 1 second here just to pull that up. So part of what we're working towards is just in general going through the process of preparing our engine to work with an editor. We have a lot of this stuff in place. However, there is a little bit more work that we need to get done before we actually can start on that. So here we go. I've got this pulled up, so let me just bring this over here. So this is a branch that I've created called Editor View Gizmo. And basically what this set of changes, there's a few commits in here. So there's an initial commit for the editor view and sort of our first shot at a gizmo. And then looks like we also did some bug fixes around that. So we're just going to kind of walk through this really quickly. I'm not going to explain it line by line. If you guys want, you can always take a look at the pull request that I am about to create. Tammin, good evening. Yeah, no face cam. Yeah, I tried resetting the OBS input. I mean, I suppose I could maybe delete it and re-add it, but it doesn't seem to want to work tonight. And I'm not 100% sure why, to be completely honest. The only other thing that I could, try at this point, I think, well, I guess let me try removing the source and re-adding it. Oh, there it goes. It looks a little frozen though. So is it just me or is that not animating at all? Yeah, I think my driver might just be borked or something. Yeah, I tried that to get it to work as well, just removing it and re-adding it, but it doesn't seem to want to do the thing for some reason. So yeah, I'm not really sure what else I can do. It looks like the source itself is just messed up, so I'm gonna just remove that for now, and we'll have to proceed without it tonight, and I'll troubleshoot it off camera. Yeah, at least you got a screenshot, right? So, couple things here. We reworked the way that the renderer creates geometry. So for a lot of our different systems that we have in place, we have this sort of life cycle of create, then initialize, then load, and then unload and destroy. And geometry wasn't really following that pattern, either in the geometry system or in terms of how the renderer dealt with it. So we're going to take a look at the renderer front end first. And so the renderer front end now has a couple of changes where we have a renderer geometry create, which is responsible for providing all the information to the renderer about what geometry it can expect, the format of the geometry, and so forth. And then we're going to have a separate step to upload that geometry. And that just gives us a little bit more control over how we handle geometry, just because we're going to need that control, as you'll see here in a bit. So what we've done is we've gone ahead and split those two steps out. So when we go to upload the geometry, all we have to pass now is just the pointer to that geometry, okay? One other thing that we needed to do as well is, since we're going to be in a situation where we're going to be using the same shader in different render passes, so we're basically going to have to bind the shader again, we had to split out some of the logic for the global aspect of the shader. Specifically, whether or not to update the descriptors, the global descriptors for our shader. So currently our local or instance variables in our shader require a Boolean to be passed as to whether or not it needs an update. And it's up to whatever the caller is to understand whether or not that's been used or not. And we now need the same thing for globals, because we are going to be using a shader more than once, okay? So we've added that, and I'll show you the back-end changes for that. The renderer types INL is basically just supporting of those changes. So we have the new geometry create method there. And then, let's see, the geometry upload is here, right? So as far as the front end is concerned, all we have to do when we create is just pass through the plugin and the geometry to the back end, and then when we go to upload, that's when we actually do this, right? So there's a little bit of a translation layer there that happens. The other thing is, I think most of this is actually just stuff getting moved around. Here is the apply globals. This draw versus destroy, I'm not 100% sure why it's finding that as a different change, but not really much change there. So there's that. That's the interface from the front end to the back end. As far as the actual front end changes, we'll kind of dip into those real quickly here. So the create now stores the vertex count, vertex element size, index count, and index element size, as well as the indices and the vertices themselves on the actual geometry object. So those are no longer stored in the back end. What this means is that we can actually use this to generate face data or get face data from a geometry that's been loaded. So if we ever need to do like triangle hit detection or something like that, we've actually got access to that now. So we've offloaded all that onto the front end to actually handle that. So all upload does is we have this new render geometry upload. You just pass the pointer to that, and it calls the backend version of that, which already has all the information it needs from the geometry itself. And that's really it, right? So on our debug geometries, or debug box 3D, our debug grid, and our debug line 3D, all we had to do here was, instead of the render geometry create also doing the upload, it's just split into two steps. So we just had to add a call to render geometry upload. So we just did that for those three places. So that's that. Resource types, again, to geometry, we've moved, I should say, the vertex count, element size, and the array of vertices, as well as the index count, the index element size, and the indices array to the geometry object. So that's the structure change for that. Terrain, again, we just added a call for geometry upload. Geometry system is basically, it's a very similar idea. So here, when we create the geometry, we did add a little bit of troubleshooting here. So we want to make sure that we have a valid pointer. And then we call the render geometry create. And if we don't successfully return from that, then we go ahead and invalidate the geometry, as we were doing before, but now we just have to kind of do that twice, right? So we have one for the create and one for the upload, and then the error cases for that. So that's that. The material system, basically, when it calls shader system apply global, we just pass a true to that. The shader system looks like, I think this is all actually just auto formatting, because this is kind of an old file that we haven't touched in a while. So I think the auto formatter got this one. The only difference here is we changed from a parameter type of void to Boolean needs update. And that's really the only thing that we had to do there, right? So it's mostly just changes supporting those two things. This is mostly formatter stuff until we get here, where we have the apply global again. We just add that Boolean, and that's it for that one. Okay, the editor gizmo, I'm going to come back to that and explain that. So there's the header file for that. And then this is the new view, so I'll come back to that as well. I'll come back to game keybinds, because that supports some of the changes that we've added. Game state was basically just me adding an editor gizmo. We'll touch on that in a second. The simple scene, let's see. I think this was just me fixing some formatting stuff. Typo here, fixing what packet was being referenced and things like that. So that's mostly just fixes for that simple scene. So there's nothing really major in there. Testbed main does have quite a lot of changes in it. So we'll kind of come back to that once we go over the other stuff. Testbed types, we added a new entry into our enumerator for the editor world. So Basically, our packets are going to be processed in Skybox. Then we're going to do the world view. Then we're going to do the editor world, which is sort of an overlay on top of that. Then we'll do the UI, and then we'll do the pick pass, right? So we sort of just inserted that into the middle there. And then this is the render view pick, which this is just doing some data validation here. Updates for apply global, just like we've done in a few other places, so nothing really major there. And let's see. So render views, all these render views basically are the same thing, right? So they're just using this render global, the new version of that, and adding true. So that's that. In the render view world, we are actually having to update the shader render frame number, and this is a bit of a hack, so that we can tell whether or not that shader has been used. So we really need to come up with a better way of handling that. Our shader system doesn't really have that at the moment, but that's the same technique that we use in our material system to tell whether the material shader has already been used for a particular instance, right? So this is kind of the same thing. Vulkan backend, that's going to be a pretty big change for the other stuff that we've done. So we have our geometry create and upload here, and our destroy and our draw. And then, of course, our update to apply globals. So I guess we could probably step into that, but let me hit these other couple files here first. So Vulkan types, from the Vulkan geometry data, we have removed the vertex count and the vertex element size, and the index count and the index element size, right? So that's a much simpler object now. It's literally just IDE generation, the vertex buffer offset, and the index buffer offset, and that's it, right? Which is arguably what it should have been from the beginning. Okay. So the other thing is our plugin main.c, we're just wiring up our function pointers, right? So the function pointer for upload, vertex update, draw, we're just wiring up those changes. So now let's talk about the back end. So the back end is basically this the same changes that we've seen elsewhere. So we're just going to take a look at the implementation of that. So the H file there doesn't really give us anything new, but the backend .h or .c file does. So as I mentioned before, instead of create handling all of this, now it just handles the plugin and the geometry. So this particular backend doesn't actually do anything at that phase, right? It's mostly in the front end that a lot of the copy work is done, right? But if we needed to, we've gone ahead and exposed a backend function equivalent for that, just in case that's what we need to do. So the geometry upload is handling most of what the create handled before. I did offload this vertex count and vertices check to the front end, since the front end is what's saving that off. As well as I went ahead and removed all this old range logic, because we don't need that, right? We actually have a separate thing for that now. So all it does now is it determines if it's a re-upload, and if it's a re-upload, then it already uses the created buffer. Otherwise, it creates a new slot and rolls that way instead. Here I'm just fixing, changing this back to be one line. So here is the vertex data. So if we are not in a re-upload, then we go ahead and reallocate or allocate some buffer space. Painzen, thank you so much for the follow. I appreciate that. So if we're not re-uploading, obviously we have to allocate some back-end render buffer space, right? So we go ahead and do that here. Otherwise, we can skip that step. And then we actually load the data here. So we just call render buffer load range, and that just passes all that data back to the GPU. The index data here, basically, if we have an index count and index data, and obviously an index size, right? So if we meet all of that criteria, and we are not re-uploading geometry, right? So it kind of falls into the same thing. So if we meet that criteria, and then if we're not re-uploading, we allocate space from the buffer. Otherwise, we can skip that step and load the data, right? So it's just vertex, then index. And then we don't need to free any old data. That has all been moved off and is separately doable now. So we don't manage that anymore. That's all gone. Here was we basically switched things from being the internal data to the geometry for vertex count, size, things like that. So that's basically what all of these are. Plus, taking things from being multi-line like this and trying to put them on a single line. So that's basically what all this stuff is. Draw, again, multi-line to single line. Nothing really new here, right? This is all just formatting stuff. Apply globals. So apply globals is mostly the same code. The only difference is and this looks like a lot more code change than actually is, but basically what we've done is we say we get convenience variables for our command buffer and our global descriptor, and then we say if we need to update, then we build out all of our descriptor buffer info and our descriptor rights and all that stuff. And then obviously update the descriptor sets. If we don't need to update, then the only thing we do is we bind those descriptor sets, right? And so that's that important split out that I was talking about, because you can't update a descriptor set more than once, right? So this is the way that we detect whether that's already been updated, and update it if it needs it, don't update it if it doesn't need it. So that's the back end. It looks like a lot more than it really is, mostly because of the formatting changes. Let me see. Lately I've been working on ECS and wanted to hear your opinion. What do you think of reserving 12 bits for generation, counting in each index 40, 96 possible generations? Is it too much or not enough? I would say start with the most reasonable amount that you can think of, because you can always increase it later. But if you're reserving too much, then that's kind of a waste, right? If you feel like it's too much, I would say cut it in half. Start there, and if you need to increase it, increase it. Okay. So that's all the back-end stuff, all the render of front-end changes. So now let's talk a little bit about the Gizmo. So we briefly talked about the Gizmo on the last episode, and I don't know if I have... Let's see if I can find that image again that I had. Okay, here, I think this one's it. Yeah, this is it. If I can drop it onto the window correctly. All right. So this is kind of what we're looking at creating. We're not going to make it exactly like this. We're going to make it similar. So this is the editor Gizmo out of 3D Studio Max. And so this one has 3 modes. It has a translate mode where you can move along the X, Y, and Z axes. Do note that Z is up in this case instead of Y. So in our engine, Y will be up. Then we have a rotation gizmo, which looks completely different, and a scale, which looks completely different. So this is what we're going to be making more or less tonight, right? And then we're also going to have a 4th mode that we're going to call the none mode. And that none mode essentially is going to just be a mode that doesn't allow you to do anything but see where a selection is, if that makes sense. So that's basically going to look a lot like this first one here, except it's just going to be gray axes, right? So that is what this gizmo is. So let's actually look at the header file first. So here are the modes that we have for our gizmo. So we have none, move, rotate, and scale. And then here is the gizmo mode data. So we have data for each individual mode. And then here's the structure for the gizmo itself, right? So the gizmo consists of a transform, the mode that we discussed up here, and then one of these mode datas per mode, right? And so what we're going to wind up with is basically a list of geometry, and we're just going to swap out which one gets rendered at a time. So each mode's data just holds vertex information and potentially index information, and then, of course, a geometry structure. So what that's going to leave us with is the ability to quickly toggle between them and not really have to worry too much about rendering stuff, right? So, of course, like a lot of other things, we have a create, destroy, initialize, load, unload, update if we need it, and then a Gizmo mode set. So the interface for this thing is pretty lightweight. And all we have here are, under create, we basically just set up our array, just basically kind of zero stuff out, set things to defaults, that type of thing. Our destroy doesn't really do anything yet. We will in a bit. Ooh, ads. Just get a break for ads, that way we don't miss anything on the stream. So we got just under a minute. Let me actually edit the stream info real quick. Okay. So that new stream title will give us give a little hint of some of the stuff we're going to dive into tonight, but we are back. So basically I was just saying the destroy method doesn't really do anything right now. We'll come back and clean some of this stuff up later. We're just trying to kind of get features in really quick right now, right? So initialize sets our mode default to none, and then goes through and creates each one of the modes. So we have one for none, move, scale, and rotate. So what these do is they basically set up all of the geometry that we're going to need without actually loading it, right? And then our load goes through each one of our modes, creates our geometry, uploads our geometry, and updates the generation, just like we've done with a lot of other geometry, right? So that's all the load does. The unload technically doesn't do that yet. We probably should, but it's just not doing it yet. Update doesn't really have to do anything just yet. I suspect that it will, though. And then all this Gizmo mode set does is just flips the mode here. I added this as a function just in case there's any other sort of logic that we need to do on a switch. But I think for now, this should be sufficient. So what each one of these modes creation methods does is, first off, it grabs a convenience pointer. We determine what the vertex count is, allocate the vertex array. And in this case, for the none, we just have a gray color that we're going to use for everything. And then in this case, all it does is create 3 lines, essentially. So we create 6 points for that. And since we're dealing with a line list here, as we discussed in the last stream, we don't need any index data. So all we have to do is have vertex data. And that's going to actually be true so far for all of these modes, right? So that's none. The move mode but does something very similar, except each axis is colored. R for X, G for Y, and then B for Z. And then we have these individual sort of like these box lines, which are these guys here, right? And those help us grab more than one axis at a time. So that is what these are. There's 2 for X, 2 for Y, 2 for Z, right? The scale is also pretty simplistic. So we're actually not going to make quite this many lines. For now, we're basically going to have the X, Y, and Z lines along the axis. And then we're going to have a outer sort of triangle here that sort of just blends between the two colors as it goes from one to the other. And for now, that's going to be really it, right? So here's our X, Y, Z. Here's our XY outer line, our ZY outer line, and our XZ outer line. So we may add more lines to this in the future, in which case we could just up the vertex count and we'll be golden. The most complicated one is this rotate. And that is this guy here, right? So we're not doing this outer circle for right now. In hours, you're actually going to be able to see the rings all the way through. But again, we draw very small axes in the very center. So if you look closely at this, we actually have an X, Y, and Z, a little mini one in there. So we're gonna do that as well. And then for each of the axes, we generate points in a circle. So we basically generate points along the plane of that axis. So we do Z and then Y and then X, right? And that just kind of goes around however many segments we have. We just create a bunch of lines, and that will eventually give us a circle. So we're going with 32 segments for each of the loops. That I think looks pretty good when we go ahead and render it out, right? And that is all there is to the Gizmo for now. Like we're definitely going to be adding more to this, but at least to get something up and running and on the screen, that's all we need to do for right now. So that is the Gizmo. And then the editor view world is actually pretty straightforward. So I think we can go ahead and knock out the H file first, because this looks almost exactly like the world view. In fact, it's almost a dead copy of it, right? The only real difference is we have this world packet data where we pass a pointer to the Gizmo, right? So we just forward declare that here, and that's it, right? So pretty straightforward interface there. And then all this view does basically is sets itself up with shader locations, with internal data like our clipping planes, our FOV, world camera projection matrix, things like that. All things that the world pass does, because we want to render with those same settings. And then we have the internal data here. Wait a minute, we already went over that. So we have the render view on event here, and all that does is catches our whether or not we need a render target refresh. So this is, again, just copied exactly like it exists in the world pass, right? The on register doesn't do anything particularly novel either. All it does is goes through and grabs the color shader, grabs the shader locations, sets the clip, FOV, stuff like that, generates projection matrix, grabs a pointer to the camera, and then registers for the render target refresh required, right? So there's nothing really new in here either. Same with destroy, nothing really new there. Resize is exactly the same as the other views. On packet build is the only thing that is a little bit different. And all that is we build out our projection and view matrix, and then we go ahead and cold cast the data to our editor world packet data. Make sure that we have a Gizmo. Grab the geometry for that, and then set all of our our camera position, our gizmo position, our FOV, distance, all things like that, right? And so what we do, what we're doing here actually is something a little bit different. This section right here is what differs between this and the regular world render pass. So the way that we need a gizmo to work is the gizmo needs to remain the same size on the screen no matter how far you are away from it. So if you're 3,000 units away from it, away from whatever is selected, it should appear as the same size as if you're 2 units right up next to it, right? And the reason for that is so that you have the same sort of selectability and maneuverability from any distance from the camera, without having huge controls when you're close to it and super small controls when you're far away from it. And so to do that, what we do is we get the camera position and the gizmo position, and then we get the FOV and the distance between those two positions. We then go ahead and grab the world matrix for that. We set what we call a fixed size, which I have a to-do here to make this configurable, and I'm just setting that to 0.1. This is sort of just used as a multiplier to resize how big it is at any distance, right? And then we have this scale scaler, which is used to create a scale matrix. And basically what this is we take the tangent of half of the FOV, multiply that by 2, multiply that by the distance, and then times the fixed size. And that is what gives us a constant size regardless of distance from the camera. So we take all of that, we multiply that into the model matrix before feeding it into our render data. And then we push that into out packet geometries as we normally would. The packet on destroy, there's nothing new to see in there. On render, the only thing that this really does is it uses the color shader, it binds the globals, and then it determines whether or not the shader has already run. So is the render frame number the same as the current frame number? And that was that change that I showed you before that was sort of a bit of a hack. That is what gets us around, or what gets us this needs update, right? So if we do have an update needed, then we go ahead and we set the uniforms for projection and view, and then we apply the global passing along that new Boolean. And then through here, we just loop through the geometries and draw as normal. So in this case, we don't have any instance level uniforms to be set. So the only thing we need to do is set the model matrix, which is local level uniform, and then we draw it. And that's it, right? So that's all there is to the view. The view is pretty straightforward. A lot of it is copied from other views. So we probably are going to be taking some of that duplicate logic and splitting it out into maybe a utilities file or something like that where we can reuse some of that logic. But for now, I'm not going to worry about it. Okay. So last but not least, we have game key maps or key bindings. So what we've done is initially we had the 1, 2, and 0 keys on our number strip at the top of the keyboard, bound to change the render mode to set it between default rendering mode, normal rendering mode, or lighting rendering mode. Those have been changed slightly to now also require control. So you'll have to press Control 1, Control 2, or Control 0 to get those different rendering modes. The reason for that is so that we could use 1, 2, 3, and 4 to switch the gizmo mode. So we have here some key map bindings for that, 1 through 4 with no modifier versus our 0, 1, and 2 with the control modifier, right? So that's that. And then the game on set gizmo mode basically says, okay, well, which key was pressed? Was it 1? Change to none. Was it 2? Change to move. Was it 3? Change to rotate. Was it 4? Change to scale, right? And that just allows us a very quick way to be able to swap that out on the fly very quickly and easily. All right. Last but not least, we have the changes to the testbed main, which is looks like a lot of code, but it's actually really, again, it's not. So we'll start here at the top. We've included the new view as well as the editor Gizmo. We've moved the debug console load down to below this this state where we're getting this convenience pointer. And that's because we were just doing a cold cast here and this was kind of ugly. So I just decided to sort of refactor that and clean it up. Here at the top within initialize still, we set up our editor Gizmo. So we create it, initialize it, and load it right then and there. It doesn't have any assets or anything, so it doesn't need anything else to be stood up. We've gone ahead and changed the camera rotation a bit to look where the gizmo is going to spawn. So that's what that update is. We've upped the packet count to 5 because now we have 5 views. We've gone ahead and injected that new view here right into the center of the list. So we have editor world right there. So that's just adding that. I added a note here to simple scene populate render packet that it generates the skybox and world packets, just because that wasn't immediately obvious, right? So calling this function takes care of that. We've also removed some things. So I should say we've moved some things around, right? Before we actually get to the UI, after we've done the world, we need to do the editor world. So we do that, we grab a pointer to it, set up the data, which right now just takes a pointer to Gizmo, and then call the onBuild for the packet for that. And then the UI packet, I've gone ahead also, one thing I forgot to mention. Starting, where was that? So starting here, I've scoped all of these things just to kind of separate them out a little bit more. So you'll see here that I have the UI packet, right? I've left the packet outside of that scope, but all of its logic is inside this scope. The only reason I did this is because we need it later for the pick pass. So we go ahead and do that, set up the mesh count, the UI meshes, all that stuff we did before. And that's really it, right? It's just scoped now. So this is all of that, right? This is the pick pass, which again has just been scoped. I removed some to-dos here because these are no longer valid. Here is the editor world view. And this is within render views. Sorry, I should have pointed that out. So this is in the render. Up here was the update. This is the render, right? So we do just above this, the world view, right? Here is the editor world view, right? So this is where we set up the render pass info for that. It looks almost exactly the same as what we set up for the world pass, right? So I'm not going to go over that. Should be pretty self-explanatory at this point, what's going on there. And then here I'm just removing some to-dos, right? So all of this is what is in this change set, which honestly took longer to explain than it would to probably just read all of the code, right? But I hope all of that makes sense. If you guys have any questions about that, feel free to jump into chat and I will answer those to the best of my ability. All right, so now that we have that, let me get this out of the way. And I'm going to run clean. So one tiny change that I made offline is we have this this build, debug, build, release, and clean scripts that I've added. And I added those just because I got tired of having to think all the time about all the flags that get passed to build all. So those are just convenience scripts that I added. So let me just actually quit out of Vim real quick and reload that. And I'll go to build debug so that we can see where we're at so far. And I'll go ahead and just grab VS Code here for debugging purposes. I'll just run this guy. And so now we see, without even loading a scene or anything like that, we have our Gizmo here. So we can kind of, take a look at that. And, no matter how we move around in the scene, we never really get any closer to it, right? And so I can hit, if I hit 1 on the keyboard, that's the same thing as what's there. That's sort of the none mode. If I hit 2, then we have our sort of move mode. If I hit 3, we have our rotate mode, right? And again, as I move around, we can see how that rotates, right? And of course, if I hit 4, then I have our scale mode. Oops, right? So there is our scale gizmo right there. So if I go ahead and load up a scene, we can see that the gizmo is always on top, right? So the grid and all that stuff isn't necessarily, but like we can see the gizmo through the walls. And that's the reason we have a different render pass for that, right? And so we can switch this, and no matter how far away we are, this always remains the same on the screen, right? Which is super important. So that is those changes. And the reason I did most of that off camera is because I didn't think it was all that valuable to sort of go through the process of that, right? I figure this is probably significant enough, right? So if we wanted to look a little bit bigger, we can see that here, right? Okay, so that is all those changes. So what I'm actually going to do is, we already have this here. So I'm just going to create a pull request. That's going into main. I'm going to merge this stuff in now. That way you guys will have access to that branch. All right. And what we're going to do now is create another branch. So actually, let me go to pull all that stuff down, and then get checkout, new branch. Let's call this feature Raycast, which gives a hint as to the next thing that we're going to be talking about, which is raycasting. What is raycasting, you may ask? Well, raycasting has a lot of uses, but basically the primary use in our case is going to be for object selection. Now, we do have our pixel perfect selection that we've added before, and we could certainly use that. But we're going to need raycasting for a number of things in the engine, and I think it's about time that we add it. So let me fire up good old GIMP here. And bust out the paintbrush. Yeah, that should be big enough for you guys to see. Okay, so what is array, right? Sorry for my terrible handwriting. You know what? I'm not going to do that this time to you guys. What is array? Well, array is... go away. All right. Array is basically a line in space that originates at some point. Why can't I draw? Sure. So we have a point at, you know what, let me actually draw a little graph here. right? So let's say we have, just an XY plane. We'll talk in 2D now, but the same concepts apply in 3D. So you have a point somewhere in space, right? That looks like this. An array is basically a point of origin and a direction. That's it. That's all array is, right? And so it basically starts at this point called the origin, and it just proceeds off into space infinitely in a single direction. What is the purpose of that, right? Well, the purpose of that is to say, what in the world is intersected by this particular ray, right? So let's say we've got, a few objects in the world, right? We've got, some rotated boxes, some weird shapes, whatever, right? And we've got one here. And we also have another one, here, right? And so what we're going to use this for is to essentially look at all the objects that are in the world and say, what does this ray intersect with, right? And what we'll get is a list basically saying, okay, well, here's object A. Here's the first thing that we've hit. And the distance from here to where it hit is this line right in here, right? And then the distance to the second object is here, right? And so we'll get a list of 2 objects back in this case that we've hit. And the usefulness of that is that we can actually take this system and do a little bit of matrix math and use it to pick things using a clicked on point in the screen. So when we talk about object picking, this is the sort of 2 out of 2 way to do it, right? On the roadmap, we said we were half done with object picking. This is the other half. So essentially what we're going to do is we're going to implement this tonight. So before we fully jump into that, I want to briefly discuss how this is going to work. Because as you may be aware, your screen is in 2D coordinates, yet your world is in 3D coordinates. So how do we take a 2-dimensional mouse coordinate and translate that to a 3D world coordinate or a 3D ray that we can shoot out into the world and say what collides with this? To do this, we have to think about what we're currently actually doing to get our 3D objects in our world translated down to our 2D screen space, right? And so ordinarily what we have is we have what we call local space, right? And this is sort of the model, if you will, right? Or the individual object itself, right? So we go from local space. And we take a matrix to convert that to world space, right? And that matrix is the model matrix, right? So we get this world matrix, and that brings us into world coordinates. From there, we then have to convert that into what we call I space, right? And this is essentially the position, This is essentially the position of the camera, right? And so that is what takes us from world space into the space that the camera is looking at, right? So that gets us one step closer. From there, dang it, I keep selecting the wrong layer. We have something called clip space, And clip space is basically the the space within your clipping planes that you define, right, within your projection matrix, right? And so from there, you have yet another transformation that happens. Right? And that transformation is something called NDC. And that is for normalized device coordinates. So when your GPU is basically ready to, when your GPU is getting ready to output to the screen, right? This is sort of the final step, or I should say the second to final step. So basically it takes everything up to this point and puts it into a normalized space. And that normalized space is -1 to 1 range in X, Y, and Z coordinates, right? So it just takes everything that you've done so far and converts it to this range. Whoops. Okay. So we have that, right? So that's what that means. So finally, we go from normalized device coordinates to let me move this so you guys can see it. Viewport or screen space. And this is where you finally get that XY, the individual rendered pixel that shows up on the screen at some given coordinate, right? And so you have to go through all of these transformations to get 3D objects to show up on the screen in 2D. Because remember, your screen is only 2 dimensions. So what does that then mean that we need to do to implement raycasting / picking from the screen? Well, essentially what that means is we have to reverse this process. So what we do is we basically just start at the bottom. Oops. Start at the bottom and work our way all the way back to here. Right? And that is what allows us, well, actually, technically, we don't need to do, it's technically one step at a time, right? It's not like there's just one single thing that you could do. So basically, we have to take the XY coordinate from the screen, convert that to NDC, convert that to clip space, take that, go to iSpace, then to world space, then to local space. And then at that point, we'll have a ray that we can use in 3D space, saying, okay, the origin is basically where our camera is in 3D, and then the ray goes out from the screen into the world. So I hope that makes sense. If it doesn't, I encourage you to ask questions. But yeah, this is basically what we're going to be implementing tonight. This is the sort of the first step of that, right? So this is to cast a ray into the world, right? So, with all of that, I think the first thing that I'm going to do is we actually have a couple things that we need to create to sort of support this. So under our engine source math is where we're going to be working initially. And we need to go actually into our kmath H file. And I want to go down to right before where we start setting up all of our vector functions. In fact, this is probably a good spot right here. So I want to do a k inline, and this is going to return a B8. And we're going to just do a quick float comparison So I was actually surprised that we didn't have this when I was looking. So basically what this is going to do is take two floating point variables and compare them against some epsilon or some really small number and say, are they within this range of each other? And if they are, they're going to be considered equal because floating point arithmetic is not 100% accurate. There's always some rounding errors and stuff in there. Just simply using equals isn't going to work, right? So to do this, what we're going to do is we're going to take f0 minus f1, right, to get the difference between those two. And then we're going to, we're going to get the absolute value of that, which is k-abs, right? And then we're going to say if the absolute value of that is less than k float epsilon, then we're going to return true, otherwise false, right? So we could just return this, right? And so what that's going to do is just give us a quick method that we can call to go ahead and do that float comparison, because we're going to wind up needing that. So let me go ahead and document this since all the other methods in here are documented. Compares the two floats and returns true if both are less than k float epsilon apart, otherwise false, right? So we need that. And then under math, we're also going to need a new file. And I was thinking about whether or not we should kind of use it along with this same one, but I think instead of cramming more stuff in here, I think we're going to just kind of split this out to its own thing. So I want to add a new file, and I'm going to call this geometry3d.h. And in that file, we are going to basically create a couple of different structures, right? And I'm going to go ahead and create some of these structures now that we've talked about, even though we're not going to necessarily get to all of them tonight. I'm kind of hoping we do, but we might not, depending on time. So we need to include math types. And we want to type def a structure called array, right? And as we mentioned before, we have a vec3 origin, if I can spell, right? And a vec3 direction. And that is all an array is, right? Or an array. That is all a ray is, right? It's just those two things. So for this one, why did it tab all the way over there? So we'll say represents a line which starts at an origin and proceeds infinitely in the given direction. Typically used for hit tests, picking, etc. Okay. I'm not going to write comments for everything tonight just because we are kind of cramped for time, but I will probably go ahead and add comments in before I check this stuff in off camera. So the next one is going to be, we're going to go with a raycast hit type. right? Oh, and that's an enumeration. Raycast hit type. All right, and raycast hit type. We talked about rays being cast into the scene, so we need a way to verify what the different types of hits are, right? So before I discuss that, I do want to quickly touch on one aspect that we glossed over. So let's say you have a complex shape like this, right? Like this guy here. You don't really want to start off by looping through every object in the scene and testing every single triangle in that object for a hit, right? Typically what you would do is you would take the bounding box of that particular shape and use that instead. So let me just do green for that, right? So our bounding box for this typically is the extents of the object itself. This isn't going to be perfectly to scale, but usually it's a 3D rectangle. In this case, it's 2D. Where the sides would be parallel, right? I realize my drawing here isn't all that good. And we test against that instead, right? And so we have two types of bounding boxes that we could test against. We have an axis aligned bounding box, which would be a bounding box that is perfectly parallel to the axis like this, right? So this is called an axis aligned bounding box. And then we have this one, which has an orientation, scale, and position, right? And this is called a oriented bounding box. And this is the type we're interested in, right? Axis aligned doesn't really do us a whole lot of good here. Oriented is what we need because our object could be scaled, rotated, and moved, right? And so we're basically going to interact with this. So the two types of interaction we can have is oriented bounding box or something else we'll say hit type surface, which would be our second check, right? So we start off just checking for bounding boxes. And then if we have a hit with a bounding box, we say, okay, well, did we hit the bounding box, but did we actually hit the object, or did we just kind of pass through the corner of the bounding box like this, right? And so that we would call a hit type of surface, right? So if we actually pass through like this and we hit the surface here, then that's what that would mean. All right, so I hope that makes sense. If the origin is where the camera is, then it's only necessary to revert up to the eye space node because the eye space is centered around the camera as the origin. Theoretically, yes. There are some things that are kind of done for us. I'll show you when we actually get to write the code. There are some steps of that technically get skipped for us. So we have here, we're just going to call this OBB for oriented bounding box, and then raycast hit type surface, right? So that's that. We'll probably wind up adding more to that later. We might support axis aligned bounding boxes, just because that would be fairly trivial to implement, but it's not what we want at the moment. All right, so the next thing is we need to type def a structure, and we're going to call this raycast hit. So this is to represent each individual hit. So we'll have raycast hit. And what this is going to contain is the raycast hit type, which is just called type. We'll have the U32 unique ID, right? So that's going to be like the unique ID that we've been assigning to meshes or the terrain or what have you, so that we can actually identify what object we've actually hit. We'll have a vec3 position, right? So the position at where the hit occurred, and then the distance as well. So that's going to be the distance from the origin of the array. Now, technically speaking, we could calculate the distance just by taking the origin of the array and subtracting position, but that's already actually going to be done for us by the method, so why redo it? Okay. Finally, we're going to have a typedef structure again, and this is going to be called a raycast result. So what this is going to hold is a bunch of hits, an array of hits, right? Hits. And this is going to be a D array, but we're only going to create it if a hit exists. Otherwise, null. Right? So we can tell from this whether or not we actually have a hit. We're also going to return a Boolean from the function that we're going to write, but we'll have that as well, right? Okay, so we need two methods for right now. We need a externalized function that returns type of ray. We're going to say ray create. This is just so that we have a quick way to create this if we want to use it. If we don't have to. We could always just fill the properties out manually. But so that's going to be vec3 position and vec3 direction. And the other one that we're going to want is we're going to implement return type array. I'm going to say ray from screen. We need a bunch of info on in order to generate this. So we need vector2 screen position, right? So the XY coordinates on the screen where we actually clicked, right? We need the vec2 viewport size, right? So we need to know how big the actual overall viewport is. We need the vec3 origin, so that's typically the origin of the camera. We need the matrix for view, so that's the view matrix from the camera. We also need a matrix for projection, right? So that's typically going to be the projection matrix that we used to actually render the scene. We're going to use that again, right? So once we have all those things, then we can go ahead and generate an array. So I'm going to copy these guys. And we're going to, oops, come over here and create a new geometry 3D .c. Of course, include geometry 3D.h, right? And I'm just going to paste in our function definitions here. Get rid of these KBIs. Right? And we're basically just going to quickly implement these. So all this one's going to do is create an array called R. I'm going to set it to just be zeroed out for everything. R.origin will be set to position. And R.direction will be set to direction. And we return R. Simple enough. Now, this next bit is going to be our generation code to generate our array. So we're obviously going to create array, right? And we're going to return that array. So the first thing we need to do is we'll go ahead and set the origin because that could be used as is, right? And then the next thing is we actually want to, remember, kind of walk this back right? So we need to start by getting the NDC, right? So we'll say get normalized device coordinates, i.e. -1 to 1 range. Okay. And to do that, we are going to create a vector3, and we're just going to call this Ray NDC. And we're going to set Ray NDC dot x equal to 2.0f times screen position dot x. We're going to divide that by the viewport size dot x minus 1.0f. And this is basically going to take that and convert it to that -1 to 1 range, right? The next thing we're going to do is basically the same thing for the y range, with the exception of y is typically bottom up, right? So we have to compensate for that. So we're going to say 1.0f minus, and then basically the same thing. So 2.0f times screen position dot y divided by viewport size dot y, right? And then finally, the z-axis we're just going to set to 1. We don't technically have to do that, but just for the sake of completeness, that's what we're going to do. So the next step of all this is now we have to go to clip space, right? So to get to clip space, we are going to say we want a vector 4 because we want to be in homogeneous coordinates. So we're going to call this ray clip, and we're going to say vec for create, and we want ray ndc dot x, ray ndc dot y, and then we want for the z-axis we want to say basically facing forward, so we want -1.0f, and for the w we want 1.0f. All right. Next step on that is I/camera. So to get that, we're going to say vec4, and we're going to call this ray I, and that's going to be where we take the mat 4 and multiply it by vector 4. There we go. And we want the projection matrix and the ray clip. But we need to undo what is done by the projection matrix, right? So to undo a matrix, you typically use the inverse of that, and that essentially reverses the operation, so that if you apply a matrix and then you apply the inverse of that matrix, it essentially comes out to a no-op, right? Like as if you haven't done anything at all. So here we need the mat for inverse of projection, right? Now, basically what we need to do is we need to unproject the XY and change the ZW to forward, right? Out into the world. So at this point, we want to say the ray I is equal to vec for create. And I realize I probably don't have to go through the whole creation thing, but I'm going to do it anyway. So ray I dot x, ray I dot y, right? Those two properties are just copied over. We want to set this back to -1.0f, and then Since this is a direction, we're going to set that to 0.0f, right? And then finally, we're going to convert to world coordinates, right? And so all we have to do here is say r.direction equals mat4 multiplied by vec4. Vec4, there it is. We're going to take the view matrix that's provided and the ray I matrix, right? But then that gives us a vector 4 and we want a vector 3. So we're actually going to have to just do vector 3 from vector 4. Right? And then it'll give us the direction that we need. And then last but not least, just to make sure that this is all sane, we're going to say vector 3 normalize. We're going to use the in-place version of this that takes the pointer. And we're going to pass the address of ray.direction. Right? Just to normalize that and make sure that it's not anything crazy. All right, and that is basically how we create an array from screen, right? So it's not terribly complicated. There's tons of write-ups out there that you can find on this stuff if you're interested in diving deep into it. But for the purposes of today, we're not going to really do that. Okay. So we have the ability to cast rays. So what can we do with that? Well, what we're going to do in this case is we actually already have the tools. Whoops. I see I missed a 3 here. So we already have the tools to actually generate a visual of this raycast. So you guys can actually see how this stuff is working. So I will not have to invert the view matrix. And the reason is because when I obtain that from the camera, it's already inverted for me. The camera is already actually doing that work. So I don't need to invert it here. Otherwise, yes, you would have to. So what we're going to do is we're going to add a little bit of debug shapes to sort of draw out our raycast for us, right? So I think to support this change, we're actually going to have to make a very minor tweak to our input. So input.c. And I want to go to buttons, input process button. So right now, whenever we click a mouse button, we just fire off an event with what button we clicked. But we actually have, we're actually storing the current mouse XY as well. And so I actually want to include that in the context as well. So I'm going to say context.data.i16, because this can be negative if you go into, if you have like a multi-monitor setup. But since it's the same data size as this U16 here, we can kind of switch between it and it'll still line up in memory just fine. So I want to say sub1 equals state pointer mouse current dot x, right? And I'm just going to duplicate that line, change that to index 2, and change this to y, right? So that way we include that location info as well, because we're going to want that. All right. So the next thing that we probably ought to do is in our simple scene, I'm thinking is probably going to be the way to do this. So let's go to simple scene.h, and we'll go down here to where our methods are defined. So right before we actually start with all of our add methods and all that stuff, we're going to do a KAPI because we want to export this. B8 simple scene raycast. Right? Because we want to query our scene based on an array that we pass what objects this ray actually hits, right? So it makes sense to ask our scene for this. So we have simple scene. We need a constant pointer to array. We'll need to forward declare that here in a second. And then we're going to take a struct raycast result pointer, and we'll just call that result, out result maybe. Okay. Go ahead and forward declare these things. So we'll come up here and say struct ray, struct raycast result. Right? And then we'll go to, probably the simplest way is to just jump to it. We'll jump to right here. Oh, won't let me jump. Okay. There we go. Okay, so this is where we're going to put it here. So we're going to paste that definition, do away with that. All right. Oh, and I just noticed that there was an ad break taking place. Sorry about that. All right. So the very first thing that we're going to want to do for this, obviously, is to say, hey, if there's no scene or the scene state is less than simple scene state loaded, right? So if it's not loaded or the scene doesn't exist at all, we're just going to return false, right? We're not even going to bother testing anything at that point. We're just going to say there's nothing, right? So the next thing we'll do is we'll go ahead and initialize our out structure. So we'll say out results. Do we not have... Oh, you know what? I didn't include... That's my bad. Let's see. Include math geometry 3D. Okay. Hits. So we're just going to zero that out, right? Only creates if needed. We should probably also say or not out result, right? Whoops. Typed the wrong character there. Right? So, if we don't pass the pointers we need, right? That's kind of... Right? Okay. So we've got that. And now basically what we need to do is we need to iterate meshes in the scene. And we're going to have to handle this one object type at a time. So for right now, we're just going to check meshes, right? And this is probably where I'm going to leave this for right now, right? Just sort of as a placeholder, right? So I'm going to return false here, right? Just so that we can kind of call this from our user code and be able to have it available, but it's not going to actually do anything just yet, right? So I wanted to stub that out. And then the other thing I want to do is I actually want to go into, let me think here for a second. I had a couple of notes here to fix a couple bugs that I found. Yes, okay, so in Debug Box 3D, when we create, we take this parent here, but we don't actually like use it anywhere in here. We don't save it, right? Which is kind of lame. So I'm gonna say if parent, then transform parent set, and we want to pass the address of outbox xform and pass parent there, right? TGDV, thank you so much for the follow. Appreciate that. Okay, so that is that change. And let's see, what was the other thing I had to do? I think it was the same thing for line, actually. So I'm actually just going to yoink this. Debug lines 3, yeah, okay. So same thing here. This just needs to say line. Right. So that was just a couple of issues that I found that we probably should knock out and fix. All right, but the primary stuff that we want to change is actually going to be in our game code itself. So the first thing we need to do is go to gamestate.h because we need to add something here. So let's do this right after Gizmo. So I'm going to say struct debug line 3D, and it's going to be an array of these things. We're going to call it test lines. And I'm going to have a struct debug box 3D. I'm going to have an array of test boxes. Zesty System 1, first time chat. Whoa, Teach Dev with a raid of 247. Wow. Thank you so much for the raid. I really appreciate that. So, welcome everybody. So this, unfortunately my camera is actually broken tonight, but I wanted to give you guys a welcome here. Let me give a shout out to, let's see. Thank you so much for the raid. I really appreciate that. So, welcome. What we're doing here on this channel is we are building a game engine from scratch using C and Vulkan. And this is a project that's been in the works for about 2 years. And thank you guys so much for the follows, by the way. I really appreciate that. And so what we've got going here is we're working on raycasting tonight. But the goal is to create an entire engine, a 3D game engine from scratch, and then use that to build games. So like I said, this has been going on for about 2 years. It initially started as sort of a YouTube tutorial series, so you guys can find me on YouTube as well under the same handle. But then, you know, I kind of decided to convert it into a live stream format at the beginning of this year. And I figured that hopefully it would help the anybody that is hoping to learn how to get into game engine development, maybe this would give them a source of information, and maybe it'll help you guys learn how one is built, right? So let me just check on chat here. Arch Linux and MVim, yes. NeoVim is the best. So hear me out. Why not just write your game engine in JavaScript? So funny enough, I actually did write a game engine in TypeScript, which kind of becomes JavaScript. So you're not completely wrong, and I have actually done that. And actually some of the commercial engines that I've written were actually in JavaScript. So I have done. Yeah, JavaScript, yep. Disgusting, yeah. So what's this theme? So this is, are you talking about the NeoVim theme? The guy who rated is the creator of Telescope plugin? Holy crap, I didn't realize that. That's awesome. I am actually using that, so that's incredible. Yeah, I love Telescope. I'm very, very happy with it. So thank you for that. He's also part of NVim core team. Sweet. Yeah, I only switched over to using Vim probably a couple months ago, actually. Up until then, I've been using VS Code. Although I still do actually use VS Code to debug when I have to, just because I haven't got my debugger set up. But that's awesome. I love NeoVim. It's such a great project. It really, really is. Notice that you're new because of the file tree. Yeah, I really only technically use this for like creating files. I actually don't really use it for anything else all that much. Like I've got this set up to actually pull up my stuff where I can fuzzy find files and stuff like that. But yeah, I'm still learning very much. You know, I'm definitely not a super experienced Vim user. I'll get rid of the file tree. I wasn't actually even really using it. That's hilarious, though. But yeah, I'd like to eventually do away with it. I just, sometimes in a project of this size, it helps to actually be able to, you know, if I'm looking for an asset and I couldn't remember exactly what it was, or something like that, you know, it helps to kind of have that tree view on occasion. You're on the same path, yeah. Yeah, debugging with VS Code. Yeah, that's typically what I do. Yep. So this is the engine thus far. So it's nothing too crazy to look at. But this is all written from scratch with the exception of two things, which is image loading and font loading. So I've got, you know, text loading and rendering on the screen here. I've got some basic lighting, basic model loading, and now we're working on raycasting tonight. So it's the Primogen stack editor. Yeah, I mean, I got kind of used to, I now have a multi-monitor setup. I kind of got used to using Tmux, I don't know, a couple years ago, just in web dev stuff. And I don't know, I just, ever since I started using Tmux, I just kind of never really looked back, right? I could just switch over here and you know, build, and then switch back, which obviously my build's broken right now, but I don't know, I like Tmux and NeoVim setup. It's great. It's really improved my my speed of navigation, I feel like. Is it fully C? Yes, it's fully C. Everything here is C. There's no C++ at all. It's now one thing that I will mention is we do have this sort of setup where I've got a few different libraries. So I've got the main engine library, and then I've got this sort of testbed application that I have, and the testbed library, which is sort of the hot reloadable application code. And then I've got some tests and tools, and a couple of things like that, and then my Vulkan plugin here. Those are all written in C, but any of these external libraries that I shouldn't say external, but I should say any of these add-on libraries that go with the editor that I'm building, or that extend the engine, of course, could be written in C++ for sure. But yeah, everything here is written in C. And I don't plan on moving to C++ anytime soon. Thank you guys again so much for the follows. I really appreciate that. Very cool work. Congrats. Thank you. I appreciate it. Appreciate it a lot. Alrighty. So I hope my intro made sense to you guys. I'm not used to having this many people, so forgive me if I'm a little bit flustered. You're going to go write some Rust. Have a good one. Awesome. More power to you. Rust is a pretty cool language. I don't know. I still prefer C. But no hate. Awesome. Okay, cool. So I'm going to get back to it and just get a little bit further. What my goal is for tonight is to basically just visualize our raycasts. So we're not actually too far from that, so I think we should be able to hit that pretty quickly. The only thing, I don't think I declared these guys. So struct debug line 3D and struct debug box 3D. All right. So that should handle everything that we need to add to our game state. So basically, what we're going to do here is used for visualization of our casts and collisions. Right? And basically what we're going to do is we're going to create those on the fly and then inject them into our render packet before it gets sent off to the renderer, and that's how we'll get our debug shapes. Okay, so with that, let's go over to testbed main and make the changes that we need to make there, because there are quite a few. So let's see. Do I have camera? I don't think I do. Thank you so much for the follow, guys. I really appreciate it. All right, so I'm going to include, let's see, it's going to be renderer camera, and then I already have some editor temp stuff down here, so I'm going to include the shapes here as well. So resources, debug. I just moved it recently, so I'm struggling to remember exactly where it was. And then box 3D. All right. So I've got those in there. And then I think it's basically just I think I really just need to create the event handler first. I think I'm going to put this after debug event. Probably after on key, actually. In fact, I'm going to copy pasta this. So I'm going to rename this to on button up, right? So when we click a mouse button and release that mouse button, that's when we're actually going to trigger the event. So we're going to check the code and say if code equals event code button released. Then that's when we're going to do the thing. So we're going to get a U16 button, which is the context data U16 sub 0. And then we're going to switch on that. Which I'm only doing this because we're probably going to have more than one button click type. Like eventually we're going to have right click and middle click and stuff like that, and I don't want to have to write a new function for that. Because all of this that we're doing right now is in the testbed application, but once we create and stand up the editor, it's going to be pretty much just pick it up and drop it over into the editor. So I don't really want to have to re-scaffold all that stuff again. So we'll say case button left. And you know what? I'm actually going to scope this. All right. So the first thing we're going to do is extract the x and y's out of this, the screen coordinates. So context.data.i16. That's going to be sub 1. And then sub 2. All right. And then we're going to go ahead and cold cast the state. So testbed game state. State equals, and then we want to get the listener inst. And we're just going to cold cast this guy for now. Game state. All right. And then the next thing we're going to check is just like we were checking in the scene. If the scene isn't loaded, don't do anything else. In fact, we probably shouldn't do... Well, I suppose we could do this, right? Because we could have different contexts that we could be in that we may need a left button click. So I'll leave that there for right now. And say if state main scene equals simple scene state loaded. And that shouldn't be equal, that should be less than, right? So if it's not loaded, then we're not going to do anything else. We're basically going to just return false. We're returning false here because when we call an event, we want to say true if the event is considered handled, or false if it's not been handled. And in this case, we just want to pass it on to something else that might actually handle that event, right? So we're just going to return false in this case. So mat4 view, we're going to go ahead and get the camera view matrix. So camera view get. We're going to use the state world camera for that. And then we also want to go ahead and get the origin from that. So vec3 origin equals camera position get. And that's going to be the state world camera. And we're going to get the projection matrix, which for right now is kind of crappy. We're going to actually have to regenerate it. So let me actually prepend this with a to-do. Get this from the viewport. Let me check on chat here. How are we importing dependencies? So the only dependencies I have are obviously Clang being installed, because that's the compiler setup that I have, and that's what I've hooked up all the make files and stuff to call. But the only actual external libraries that I'm using is under engine right now, and then I have this vendor folder. And so it's stb image and stb true type, and they're single file, single header file libraries. So there's no extra linking or anything that has to be done. But yeah, that's it. That's all there is to it. And honestly, these are probably going to wind up being moved into our editor instead of being in our runtime code. Okay, so we're going to do mat for perspective. Our FOV, again, we're going to have to regenerate this. So we're going to say degrees to radians. I'm going to use degrees of 45.0 F. Our aspect ratio is going to be our state width divided by our state height, right? And I think those are... I believe those are integers, so I'm actually going to have to convert this one to an F32 just so that that math works out correctly. Lone Star, thank you for the follow. Appreciate that. So our near clip is going to be, I'll say 0.1 F, and our far clip is going to be, I think I'm using 4,000 for everything else. Right. So obviously, this is a big to-do. Like, we're generating this in a few places in code. We don't have the concept of a viewport yet. That's something that's kind of on the short list for us to add. And at that point, we just get the projection matrix from the viewport. But for right now, we're just using the screen dimensions and sort of just generating this thing the same across all different places. So the next thing we need to do is ray r equals ray from screen. And so let me actually delete all this stuff that's been added there. So the first thing is going to be vec to create, and that's going to be f32x, f32y, right? We already have those extracted. Why does it keep... Oh, I need to get rid of that snippet. That's really annoying. Okay. And then we have vec to create for our screen size, right? So the first thing we need here is f32 state width and f32 state height. That's it for that one. And then we need the origin, and we need the view, and we need the projection matrix. All right, and that's all we're gonna do for right now. Oh, did I not include? I thought I did. Apparently not. So include math geometry 3D. There, that's better. Okay. So all we're going to do right now is just generate that ray, and then raycast results, our result, and B8 hit equals simple scene raycast. So we want state scene. We want R. We want, oops, we want the address of our result. Right. Oh, I think I need the address of this, actually. Yeah. Okay. Oh, and the address of R. Okay. So there's our hit and then we can, do with that what we may, right? So we don't actually have anything to do with that yet. So what we're going to focus on is the else block. And all we're going to do in both of these cases right now is just kinfo. And for here, we'll say hit. And here we'll say no hit. But in the no hit case, since we know that's what we're going to hit eventually, or right away anyways, we're going to create a debug line where the raycast starts and continues to. Right? So for that we need a debug line 3D. We'll call this test line. Then we need a debug line 3D create. So point 0 is going to be the r.origin. Point 1 is going to be basically what we're going to do is we're going to take the origin and the direction. We're going to scale the direction and then add it to the origin, and that'll sort of give us the end point of that line. So we're going to say, I guess I'll kind of put this in that order. So we'll say vec3 multiply scalar. So we're going to take the r.direction, and for the scalar, we're going to set that to 100.0f, right? So we're going to extend it 100 units in the direction of direction. Okay, and then we're going to take vec3 add, and for the first vector, we're going to say r.origin, right? And for the second one, we're going to pass in that scalar that we calculated. Let's see. Where is it? 100. Okay. So there's that. And then the transform parent, there's actually not one. So in this case, we're just going to pass null. And then we will say the address of test line. Okay, so we create our line there. Debug, initialize, line initialize. And in this case, we want the address of test line. And then debug, line load. We want the address of test line again. So that's going to just load that in the GPU, right? And then in this case, we're actually also going to set the line color, right? Because we want to have a different line color for if we hit something versus if we don't hit something. So I'm going to say magenta for non-hits, right? And so we can say debug line 3D color set. We want the address of test line. And then we want a vec4. And we're just going to create this as 1.0, 0.0, whoops, 0.0. And then 1.0, whoops, 1.0, not 2.0. And full alpha, right? And then the last thing that we need to do is we need to say darray push, else something else. Thank you so much for the follow. Appreciate it. So the array we're going to push to is that state test lines, right? And we're just going to push test line to that, right? Whoops, looks like I forgot line there. Okay, so we've created our 3D line. There. Right? So we've created our 3D line, and we added it to our test lines. So this is not enough to get it to render. We actually also have to continue on down to the render block, right? But before we can do that, there is one thing that we need to do in application initialize. So initialize. So right here, after we've loaded the console, we're going to say state test lines equals darray create. And this is going to be debug line 3D. All right. And we'll just duplicate that. And we'll say test boxes is going to be box 3D, right? So we need to create those, otherwise we're not going to have a good time when we actually go to add to it, because they'll be null, right? All right. I think the only other thing that we need to do is our little bit of a hack to inject the debug geometries into the world packet. So let's go to application render. So here is where you're generating our packets. In this case, we've generated the skybox and world packet in here. So before we actually move on to, let's see, I want to do this probably do I want to do this before, or yeah, I want to do this before editor world. I don't want it on top of the world. I want it mixed in with it. So I'm going to put hack inject debug shapes, we'll call it geometries, into world packet. And in here, we're going to do U32 line counts. If I can spell, darray length, state, test, we want test lines. And then we're going to loop through that. So for U32, I equals 0, I is less than line counts plus I. And in here, all we basically need to do is set up a geometry render data for each one of these and then push it into the packet. So geometry render data, we'll call this RD, and we'll zero this guy out. And we'll say rd.model is going to be equal to transform world get, and we want the address of state test lines sub I x form. The RD geometry is just simply going to be the address of the state test lines sub I geo, and the RD unique ID is going to be invalid ID U16. And the reason that's invalid is because we don't necessarily want to be able to pick it, and we don't want to treat it as a selectable object, right? This is just a debug shape. We don't need that. Then we'll do darray push, and this time it's going to be into packet views, and then we want the sub testbed packet view world, and then debug geometries, right? And the value we're going to push there is RD, right? And then I actually need a lot of what I've typed here, so I'm just going to duplicate this line, and I need the packet views, debug geometries, change the rest of the line. We'll say debug geometry count plus plus. All right. And I think that's everything I need to do. No, it's not. I need to hook up the event. Otherwise, a mouse click won't do anything. So register. I want to register events. I'm just going to copy pasta this guy. Event code button released. We want the game instance state in this case. And then game on button up. Oh, it gave me the whole thing. I don't want all that. There. So we have that. We need the unregister as well. So we need to come down here and paste. Unregister. Okay. I think that is everything. So, let's see. Let me read chat real quick. Hello, streamer. Hello, chat. In between two options, machine learning or computer graphics programming. I started to learn both, and I found it really exciting, but I need to make a choice and stick with one direction for a career. Can you give me insights about the jobs, such as salaries, opportunities, transition? Okay. So I can't really speak to the machine learning half of it because that's not something I've done a lot of. In terms of graphics programming, if you get really good at it, there's lots of opportunity, but there's also lots of competition. And I think that's fair to say in a lot of industries. Although if you get really good at it in terms of being able to write low-level application code like Vulkan or DirectX or something like that, especially those two, DirectX 12, you could get hired on as an engine programmer somewhere, which could be very lucrative. NVIDIA is investing hard in machine learning. That's true. I just don't know enough about it to speak on it. Shiro, it looks like my bot apparently is broken, which is sweet. So what the Kohi command there is supposed to do is it's supposed to take you to this address. I'll type it out here. So it's supposed to take you to kohiengine.com, which gives you all the information about the Kohi engine project, links to the source code, links to our Discord server, all of that kind of stuff. So I would suggest that any of you guys that are interested in the project definitely check that site out. There's not a whole heck of a lot there. I tried to keep it simple, but it does have links to like the YouTube channel, this Twitch channel, obviously, things like that. So definitely check that out. Okay, so let me see. What did I miss? Geometry3D.h. Oh, I made the same typo in. Yep, I did. Whoopsie. That should be vector 3. Non-void testbed main 199. Oh. I'm going to say return false so that other stuff can handle it. It's just asking for a return type for this event handler. Okay. So, I'm just going to bring up VS Code here for my debugger. See if this works. So I should be able to basically click on the screen and have some debug geometry being loaded. I think I might have to actually have a loaded level for this to work. So I can click there and then move off to the side, and there we go. So, I can click basically a whole bunch of times on the screen. I'll just kind of circle around this little gizmo here. And then if I move off to the side, you can see all those raycasts that I just shot out. So they all start from this camera point here, and they just kind of go off into space 100 units, right? So you could probably see that a little bit clearer if I shoot off towards this terrain here, right? So it's not infinitely long, but it's long enough to give you an idea where it's supposed to go. So I think this is probably where I'm going to wind up wrapping up the stream for tonight, only because I do have work in the morning. But I think the next time on stream, we're actually going to handle the raycast detection, hit detection. So we've already got these bounding boxes here, these oriented bounding boxes around these meshes that are loaded. And so we're going to go ahead and add the logic for that next time, for sure. So, so you're not with Tej anymore, Moshana. Morushana. Hello, hello. So I really appreciate all of you guys who rated that stuck around. I really appreciate all of you guys. I hope you find this project interesting, and I hope you stick around for the future for sure, because we're going to be developing a lot of cool stuff with this. So yes, I definitely recommend you join the Discord server. It's still kind of small and growing, but you know, I think we are over, I want to say it's over 600 members at this point, I think. You know, there's a lot of lurkers on there, but I try to pop on and talk when I can. But in my absence, there's definitely a lot of people on there who are who love nerding it up just like me. So awesome, awesome, awesome. So yeah, with that, thank you guys so much for being here. I really appreciate it. Next time, I will make sure that my camera works so that you guys can actually see me, because that kind of bums me out a little bit. My camera wouldn't work tonight, so I'll have to investigate that. But yeah, I'm going to go ahead and what I'll do is I'm going to add a couple of comments in the code, and then I'll go ahead and check this in. And you know what? Actually, I'm just going to check it in as this. Initial raycast commit. All right. That way, you guys can all have access to what I've done here tonight. So, really quickly before I go, I will pull up a new tab here. This is just the pull request. I'm not going to do that for right now. But let me go to kohiengine.com actually. So this is the site that I've created for the project. So we've got YouTube, which basically all the streams here are archived on YouTube. So I do have to give it, I think it was either 24 or 48 hours, I forget. But I basically schedule out the updates on YouTube. I upload them like 1 or 2 times a week. And then, of course, I Twitch stream every Wednesday and sometimes Thursdays as well. But yeah, this is some information about the project. The Discord link is here. In fact, I will copy that and put that in the chat as well. There we go. And the GitHub project is right here. And of course, you know, I have to plug my Patreon, right? So if any of you guys, if you guys like my work here and you want to support me, that is one way to do it, or through YouTube memberships. All of the funds for that get poured right back into this project. So for example, I actually bought a Macintosh computer so that I could port this engine to Mac. So we do officially support Windows, Linux, and Mac with this. So yeah, you know, I can always, you know, upgrade my audio equipment or lighting equipment or camera equipment apparently, and all the funds are used for that. So cool. All right, let me see. I'm going to see if I can find somebody to raid. unless you guys have any suggestions. Let's see. I'm going to raid Strager's channel. Strager is he's a programmer that gives a lot of help to new developers who are trying to learn things. A lot of times on his stream, that's like solely what he streams for, is to like answer questions for people and help them out with problems that they're running into. And I think it's a really cool channel. There's a lot that folks can learn from him for sure. So I'm gonna go ahead and raid him for tonight. And thank you guys so much for joining, and I hope to see you guys here next time. And have a good one.